Hi, iGen. Welcome to Project Flora, part of iGen 230. I'm joined here today with Adi, Meena, Sanjana, Kaushik, and Kayla, and we're going to be talking to you about our project.
In 2016, Canada disposed of 25 million tons of waste. All cities, universities, and public areas have a waste collection and management as a part of their infrastructure, but these systems remain largely the same as they were decades ago and are usually done according to a standardized schedule. But here's the problem: garbage bin fill levels are subject to variation every day and on a seasonal scale. So, standardized schedules may seem like an inefficient way to approach collecting waste. How full a garbage bin is depends on variations of foot traffic due to local events and weather forecasts. Collecting only half full waste bins is not optimal for operations.
Running inefficient routes can rack up costs of over $30,000 annually. In addition, there are environmental implications as these trucks emit over 20 tons of greenhouse gases annually and only get about 1.9 kilometers to the gallon. Constraints which affected our product development were the material and shape of dustbins, as well as local weather and plausible power sources. The requirements of our project were simulating readings from bins and having weather-resistant casing, taking these readings and processing information at least twice a day, and making the transmission of our data completely wireless.
After adequately recognizing the problem and a dire need of a sustainable solution, we came up with a device that can quantitatively measure the contents of a trash can and transfer that data to a network from where it can be viewed by people using a dashboard. This solution comprises of three main parts. Firstly, the hardware. The hardware of this device comprises of ultrasonic sensors, the Arduino, and a connectivity module that can send data to the network. Secondly, the software, which includes the program of the Arduino that can collect the actual data from the trash cans, and secondly, a way of transmitting that data to a network for further processing. And third comes the dashboard. The dashboard is the client-facing solution where people can view the data collected and use that data to optimize their garbage collection routes.
The CAD model was designed to be 3D printed and to be the external hardware casing which contains all of the electrical components. The case is a simple design which features an upper casing, lower casing, and intermediate O-ring. The lower half of the casing features two extrusions where the ultrasonic sensors sit in order to take readings of the levels of the bins. These extrusions have surrounding rings offset from their opening on the exterior side. This detail is to act as a barrier for collecting water such that it will not come in contact with the ultrasonic sensors. Each half of the casing has a half-circle sweep cut, which allows for an O-ring to be fitted in between the components when they mate. By having an O-ring in the assembly, we can further waterproof the product, which is beneficial in Vancouver's climate. The two halves of the casing are connected by 4 bolts, which go through pill-shaped through holes. The purpose of these pill-shaped holes is for ease of assembly. The overall size of the hardware was determined from measuring the electrical components and which configuration allowed us to minimize the size in terms of manufacturing benefits. Because we are 3D printing this model, by reducing the size, we reduce the time for printing, we reduce the amount of material which we use, and we reduce the overall cost. The box has a slight taper and rounded edges to prevent further water collection.
So here is a depiction of the circuitry that will go underneath the casing. You'll notice we are using an Arduino Uno here, but actually we are not using this microcontroller, the ESP8266 Amica, because it has an integrated Wi-Fi module plus slightly less power consumption. We have 2 ultrasonic sensors to cross-validate results. We have analog digital we have a digital logic converter because to interface the ultrasonic sensor and the 3.3 volt microcontroller. We have also we also needed a power supply because the microcontroller is 3.3 volts and it's incapable of supplying the 5 volt needed for the ultrasonic sensor.
Under the void function setup, we define the pins attached to the Arduino and the ultrasonic sensors. We set the height of the garbage bins to be 30 centimeters, but this value can be changed depending on the bin's height where the device has been installed. We also created a new text file named data where we store all the sensor readings. This file will then be sent to a server that processes the data and visually displays it on the dashboard. In the void function loop, we have a 6-hour delay as we need to take the sensor readings only 4 times a day. In the function sensor readings, we run a for loop that reads the distance 5 times with a 1-second delay between the readings. We first ensure that the readings are within the specified range and then calculate the average of the valid readings. The average distance is then converted into a percentage that represents how full a bin is, and this value is also printed to the text file.
So right now we're looking at the dashboard. You can see the city of Vancouver here. Each individual pin icon, like this one, is representative of a different bin. If we focus our attention to the top left corner, we can see the historic data of how the bins fill up. Now we can leverage this data and make future predictions on how the bin could fill up in the future. Now this allows us to make rough estimates and predictions on how we can optimize operations and when we can collect the bin at the most appropriate time without wasting any time and resources. Now, if we focus our attention to this tab over here, an operations manager sitting at a university or working with a city can add their staff and their fleet. And once all of those parameters are taken into account, we can optimize the routes accordingly. Now, we'll get more into the mathematical model of how that's achieved. The vehicle routing problem is similar to the famous traveling salesman problem. There are many variations of this problem, and they're based on different assumptions. Now, for Flora's case, we're using something called the capacitated vehicle routing problem / time window, and this means that the vehicles have a limited carrying capacity of the goods that must be delivered. Now, at each location, there's a demand corresponding to the quantity of the item that should be picked up. Furthermore, for this example, we're going to be displaying the code in Java, and we're adapting it from Google's open source tools for software development for vehicle routing specifically. Now, graphically, seen somewhere down below, for each location on a route, the output shows the index of the location and the total load carried by the vehicle when it departs from the location. Lastly, we adapt these findings in the backend of the Flora dashboard to suggest more efficient routes to the client. Given the fill level data that would be received from Flora's monitoring device, we equate that fill level to the demand variable. This in turn considers the urgency to collect more full bins sooner and gives us the ability to ignore less full ones for less frequent collections. Ultimately, doing collection only when required is a reflection of the percentage savings mentioned in the executive summary.
We tested multiple aspects of the device, such as the mounting mechanism, power solutions, and climate proofing. One of the biggest challenges we faced was to find a cost-effective, yet sturdy and strong mechanism to mount the device to the garbage bins. The mechanism should allow it to easily remove the device to replace the batteries or in case of defects. We explored a number of options such as industrial-grade suction pads, Velcro pads, and even magnets, but in the end, we decided to use hooks as they're strong, cheap, and can support large weights.
So now, coming to the electronic components, for network connectivity, we considered options like LoRa, which was too expensive, and Bluetooth, which was too short range. We decided we needed Wi-Fi. And for this, we chose a microcontroller ESP8266 Amica, which was widely available and cheap. When we were physically testing the ultrasonic sensor, we realized it needed a 5-volt power supply, which the microcontroller we now chose could not supply. It's a 3.3-volt microcontroller. To deal with this issue, we were considering options like interfacing an Arduino Uno plus the Wi-Fi microcontroller, but this would consume too much power. So we settled on getting a dedicated 5-volt power supply and bidirectional 3.3 to 5-volt logic converters.
We made some modifications to our code in order to test the ultrasonic sensors with Arduino. We made it so that the initial reading of the sensor would be set as bin height when the bin is empty. We also made changes so that if the distance between the top of the garbage and the sensors is within the acceptable range of 0.5 meter to 2 meters, the reading would be recorded on the serial monitor every second. As you can see, the ultrasonic sensors can successfully detect when the bin is getting full.
The presented solution aligns with the sustainability goals set by the UN, which help solve a crucial problem that may seem insignificant but is not. UNESCO Goals 9, 11, 12, and 13 aim at making communities and industries more environmental friendly by reducing greenhouse gas emissions and promoting green energy. By reducing the number of times garbage collection occurs, we could reduce fuel consumption and use that time and money where it's more needed. A case study in Philadelphia attests to saving about $280,000 in operational costs and about 130 tons of fuel annually by optimizing garbage collection. The time needed for garbage collection also decreased 30 to 50%. Hence, this innovative device can make the process of garbage collection much more sustainable, and the case study is proof of all the benefits it can provide to everyone.
With all that said, it is important that our idea does fit the market, so we conducted interviews in small focus groups with operations managers at universities or sub-entities of universities, and we do in fact see the need for a more efficient approach to waste management going forward. So what now? Our future plans for Flora include a test pilot program at a university campus. This is to ensure all the sensor readings are accurate and all the connectivity modules work accordingly. We hope that we can use some of the feedback from the according stakeholders, like operations managers at universities, to better our model, better our dashboard, and gain valuable feedback to improve our system going forward.